Hi, Sumner. We have you here. Whenever your talk comes up, you'll be able to share your slides then.
Okay, thanks. Yeah, the first time just now you just said it. My video's on. You can see it, so I'll stop video and I'll mute myself.
Great. Thank you. And we are unmuted. You can advance to it.
Okay.
Graphics told us that we're pull-ups models are crap. Oh, but then 1A.
This is 1A.
I'm just saying, maybe. I've heard about the new for Degenerates.
Yeah.
It's all the rage. It's all the rage.
These don't collapse. We're good.
Oh, sorry.
Without further ado, take it away, Abigail.
All right, everyone. So thank you so much for inviting me. My name is Abigail Poland. I'm a postdoctoral fellow currently joint between Caltech and Carnegie Observatory. And I like to describe myself as a general transient theorist. I like to try to do all things transient theory, but while constantly keeping in mind, how do I make my theory testable? Normally that involves producing observational signatures of my theories with radiative transport modeling. I'm one of maybe about a dozen of the developers of Sedona radiative transport code. But as you'll see, hopefully in this talk, if I don't run out of time, that can mean many, many other things of connecting models to the real world. I want everything I do to be falsifiable. So I was asked, the slides do not advance.
Click once on the.
Gotta go back. Or, nope, sorry. This is not updated.
Oh, no. I think this is the problem.
Yes, well, while you fix that, I'll continue.
You're pausing.
Oh, well, thank you. Okay, I can see I'm already missing a slide anyway.
Sorry, it seems to be happening again.
That's all right.
Okay. Then I'll complete. Otherwise, we would say we should get hook up your laptop now.
Yeah, if only. All right, well, I'll talk while you try to fix that. So I was asked to come here today and talk about connecting the models of type 1A supernovae to what's actually going on.
Do you have-
And
do you have
most, yeah,
Animations.
I do have animations with
Okay.
the problem.
Shucks.
Yeah.
You can just share maybe this the window. Does this work? Just continue.
Okay, yeah, so we heard a lot during this conference about the companion of the white dwarf and not nearly as much about what the white dwarf is or how it explodes. And so that's what I'm going to focus on today. And we're probably going to skip a few slides when we catch up to it. But traditionally, we've always thought of type 1A supernovae as the explosion of a Chandrasekhar mass white dwarf. That is, yeah, I don't know if to keep talking or not, but yeah.
Make sure you have your slides. There's time.
The update was supposed to fix this.
I don't need notes.
Is
I
this
didn't
a
even realize
keynote
they were
thing?
there. It's
Yeah,
a
it's a
keynote
keynote,
thing
Zoom not jiving with the, you know.
currently.
Now.
Yes. Okay.
Sweet.
Good.
All right. So as I was saying, traditionally, we think of a type 1a supernova as the explosion of a Chandrasekhar mass white dwarf. I'm going to say from the get-go, at this point, we see enough diversity in type 1a supernovae that there is no one single model that can explain them all. But traditional picture is this guy, a Chandrasekhar mass white dwarf. It can no longer support itself via electron degeneracy pressure. So we've tried a couple things in order to blow these up and create a 1a. We've tried just detonating it at the center, but when you do that, you get too much nickel in the explosion. There are very few intermediate mass elements left. It doesn't look like a type 1a supernova. It's too bright to be a normal type 1a, and it's lacking things like silicon and sulfur that we need to be there according to the spectra. If you instead deflagrate the carbon-oxygen white dwarf, so burn it subsonically, you get almost the opposite problem. You don't get enough nickel to be bright enough to be a normal type 1a supernova, and you have this excess of unburnt material and intermediate mass stuff. So what we've come up with, what's currently the state of the art while blowing up a Chandrasekhar mass white dwarf, is including something, the delay detonation model, which basically we deflagrate for a little bit, which allows us to puff up the white dwarf, make it hotter and less dense before transitioning to a detonation and creating the nickel that we need to create the explosion. So in this way, you get less nickel. It's normal brightness. Because you puffed up first, you have density regions that create the intermediate mass elements. And you can get something that looks like a type 1a supernova. Unfortunately, we don't understand very well how this actually happens. So in computational models, this is a tunable knob. We can go everywhere in between a pure detonation and a pure deflagration. And we do, because that's what's important to do for modeling, right? You start with, let's look at everything and see what happens. However, we've pretty recently had a breakthrough. We've just started being able to model this deflagration to detonation transition in simulation. So this is a really cool science paper. This is lab results of the deflagration to detonation transition. This is a simulation. So over the next several years to decades, we're going to see these coming into the models, which will make them more accurate, but will also limit the parameter space of Chandrasekhar mass models, right? Because we can now no longer have any transition there. We will have them dominated by physics. So, but even when we can choose this at any point, we can't make all type 1a supernovae this way. So the next way you can look at it is, well, what if I can blow up a white dwarf below the Chandrasekhar mass limit? So a sub-Chandra white dwarf. And currently the popular way of doing this is called a double detonation. So this situation is pretty, just like the Chandrasekhar, pretty progenitor agnostic. You can, but basically what it looks like is with a carbon oxygen white dwarf below the Chandrasekhar mass, it has gotten itself a shell of helium on the surface, either accreting from a non-degenerate star like a helium SCB star, or from a degenerate white dwarf, or we've heard a little bit about the D6 mechanism, which is basically during what would be a merger between two white dwarfs, or a carbon oxygen white dwarf and a helium white dwarf, you transfer a little helium to the surface of the carbon oxygen white dwarf and start this double detonation situation. So how all of these work is it turns out it's way easier to ignite helium than carbon or oxygen. So you get a helium ignition in this surface helium shell. As that shell burns around the white dwarf, it sends a compression, a shock wave, into the center of the carbon oxygen white dwarf. When that shock front converges, it compresses the core, causes the second detonation, and it fully detonates, getting a thermonuclear runaway and a 1A-like explosion. Now, I just told you pure detonations are problematic because they create too much nickel. Not in this case. If we lower the mass of a white dwarf, we've also extended the radius, right? And we have a much shallower density profile. So we can have this case where you have pure detonation, which we understand how to model, that has density regions that give you the intermediate mass elements. So this too can create a variety of types of type 1a supernovae. I have this is one of my simulations of what this looks like, so we're all on the same page. So this is the burning of the helium around the white dwarf. You can see what's clearly in its temperature, the shock wave moving into the center of the white dwarf. It will compress, cause thermonuclear runaway. And we could stop here, but my game is, what will these look like? And how can we distinguish these from the Chandrasekhar mass type white dwarfs? And so the key to this is the helium shell. So the underlying white dwarf explosion gives us the same sort of elements we're looking for in a white 1A. But the really, really big difference here is the yields from the helium shell. So this is the case of a very, very large helium shell. And when you burn it, you can see you create this radioactive material from the burning of the helium shell. And that sits on the very, very outside of the ejecta. This radioactive material is not really nickel, it's mostly chromium and iron. That's a very short half-life. It decays quickly. It's near the outside, so it has a fast diffusion time. It escapes and can create observational signatures on the supernovae that would arise from this. This is the case of a big shell. Thin shells have less material on the outside, and it doesn't necessarily need to make radioactive material. But let's together go through the lifetime of a type 1a supernova and look at what observations we can make to distinguish between these two channels. So let's start at the infancy, the first signatures we can see of type 1a supernovae. So the first thing we can look for is if we catch these really early, shortly after they explode, we can look for a bump in the light curve. Now you can get a bump from the double detonations through that radioactive decay of surface material, but we've seen you can also get bumps in other ways. So we already talked about at this conference, the companion interaction, that if the ejector runs into a companion, it can open a hole into the hotter interior. Photons can escape very quickly, you can get a bump. You can, very similar to the double detonation case, in a 100 secar mass explosion, have extended nickel profiles, depending on how long we simmer before the detonation, or even nickel shells. And that, again, for the same reasons, radioactive material having short diffusion times can give you a bump in the light curve. We've seen many, many bumpy 1As at this point, but unfortunately, a bump is not good enough to distinguish models, because as you can see here, the same bump can be fit by all of these models. So a bump can tell us a supernova is interesting, but it can't give us an answer as the progenitor channel. So we need to move on past infancy and go to the peak times of the supernovae. So at peak times, again, I'm a little biased towards the double detonations. This is what I study mostly. So it's all going to be, how do we identify one of these versus the standard assumption of a Chandrasekhar, right? That's the default. This is the weird one. So at peak times, spectra of double detonations with thin shells look normal. Spectra of double detonations with thick shells look really, really weird. We get this line blanketing happening because the thick helium shell ashes block photons from escaping in these bluer wavelengths. So these ashes are optically thick, have a significant imprint on the peak spectra. We have seen this. Our first definitive case of this was 2018 BYG. It was a supernovae, that 1A, that had an early bump and a spectra that totally line blanketed through peak. We could fit it as a double detonation with a thick helium shell. So check. This mechanism can explode white dwarfs. This event so far has not been fit with another progenitor model. This is it. The double detonation with a thick helium shell. And to date is the, I think, most direct evidence that there's multiple ways of blowing up a white dwarf. Since then, we have a lot of other cases of this, some more controversial than others. I encourage you to take a look at them. But let's look at then, if we believe this can happen, what about the thin shell cases? What about those hiding amongst our normal type 1A supernovae? What percentage of these are normal 1As, right? And how can we tell the difference if they just look normal? So in our models here, we notice this interesting trend that as we increase the mass of the white dwarf, so these different colors are different masses of underlying white dwarfs, all with very thin helium shells. So as we increase the mass of the white dwarf, we get more nickel. We increase luminosity. And we noticed we also, pretty logically, increase the silicon velocity because we're increasing the energy of the explosion with the nickel, right? While decreasing the binding energy. So we decided to see if this is a trend we see in real 1As or not, right? And we did this by plotting the peak V-band magnitude of the light curve versus silicon velocity taken at that same time of peak. For this sample of supernovae from Zhang 2018, which was chosen because they were all light curves that were, the rise was resolved from the survey. So we see here, maybe there are two groups of supernovae, right? There are definitely some that follow our luminosity velocity trend. But then there's this cluster that sits above it. And so by the machine learning techniques of our eyeball, maybe we have two groups. Here's the subchandra, Here's the Chandra-Shekhar mass explosions. When you do the back of the envelope calculations with binding energy and masses and such, that cluster does sit right around the Chandra-Shekhar mass limit, which is cool, but it's small number statistics still. So what can we do with small numbers? We can look for more ways they distinguish themselves. So again, these helium shell ashes mean some blue photons are being blocked. So these models predict redder supernovae. We definitely see this in these two classes, right? Both the models and the supernovae that fall along this trend are redder than the ones that sit in this cluster. This is cool for cosmology because these high velocity red ones that are normal brightnesses have traditionally been a problem for Hubble constant residuals. We've had to invoke weird dusty environments around them. And what I'm saying is maybe they're intrinsically redder. But I want to have a falsifiable feature too. And so that can come from the Chandra-Shekhar feature. So detonations are very efficient at burning. We leave behind very little unburnt carbon in a double detonation specifically. So if you see a carbon feature, it probably implies a Chandra-Shekhar mass explosion. And so we have the carbon feature is unfortunately really hard to detect in the optical. It is right next to this very broad silicon feature here. So this is a figure from Wire 2014, pointing out all of the 1As that have a measured carbon absorption feature in the PTF sample. When I put them on this plot, they all sit in the Chandra-Shekhar mass cluster. So our story is so far consistent, but not necessarily sufficient yet, right? I have an undergraduate working with me right now trying to do this same analysis for the entire ZTF sample that's been published so far. So we'll see if it remains consistent. But let's move on in the lifetime of the 1As and in the time of my talk to the nebular phase. This is one of my favorite things to model because it's see-through and easy and fast. But if we model the double detonations in the nebular phase, we show they all have a strong contribution from calcium to emission. I'm going through this pretty quickly, but in some 1As we see this, in some we don't. When we look at some of our events that we identified from earlier features, some of them do show strong calcium. So this is 19 YVQ, which we identified as an early bump. So it was immediately of interest. We could later compare this to the nebular phase spectra, which had stronger than expected calcium-2 double detonation. There's 2016 H&K, which is actually kind of a transition between a 1A and a calcium-rich transient, but this one has the line blending followed by calcium emission. So these both fit really well with the models of the double detonations. So combining these different effects is very powerful. But again, I want something falsifiable. So we can find out, yeah, it still works with the parameter space. But falsifiability. So in the nebular phase, we need to move to the infrared in order to have something that can rule out a double detonation for an individual event. And that is found with this feature in the infrared around 19,000 angstroms of stable nickel. So in order to get stable nickel in explosion, you need really, really dense interiors. So a Chandra-Shekhar mass explosion. So these are models. Now there's no stable nickel in the nuclear network of this red thing. So of course it's not going to have a feature, but these models from Wilk 2018 show that, yeah, the higher mass, higher density core, the stronger this feature is. And we can go look at these in the infrared. So I have a campaign on Magellan working with the wonderful graduate student here, Sahana Kumar. So I've PI'd something like 16 nights on Magellan, where we try to get simultaneous optical and near infrared spectra of type 1A supernovae, because this will either tell us this event had strong calcium, or in this case, a stable nickel feature. And Sahana is pulled onto this because she is the expert in the infrared. If you were looking to hire a postdoc, she is graduating this year. She has something like 20 nights of Magellan experience under her belt, not including our campaign, and a 3-semester Magellan Gemini PI proposal. She's fantastic. Keep an eye out for her. But let's move on. This is a remnant conference. And in my last couple of minutes, let's talk about remnants, right? We've heard so much during this conference of how do we look at a 1A remnant and tell what type of 1A went off. And we've heard a couple things you can do. You can try to actually constrain the mass. You can look at what's being shocked. And you can take, X-ray spectra and do compositions. But these are hard measurements to make. And honestly, yields are hard predictions for me to make. So it's messy on both ends. So I want to take off my nucleosynthesis hat and put on my fluid dynamicist hat, right? And say, when I look at this as a fluid dynamicist, I see turbulence. We can probably understand turbulence, right? When I look at Cassé, though, I see turbulence, and I see larger scale features that probably aren't dominated by turbulence. They're probably dominated by something intrinsic to the supernova. And when I look at Crab, I see turbulence, large scale features, and an engine. And I've been doing some work with Paul Duffel and Dan Milosavljevic at Purdue, trying to ask if we can find a way to quantitatively characterize the physics under different angular mode scales here. And the concept is very simple, right? It's, what if I decompose this into spherical harmonics? What if I look at the power spectra of supernova remnants? It worked for the CMB, surely it can work for us. But the reason it works for the CMB is because we had templates where we said, we understand the physics at different angular modes, what drives it, and if you see that physics in the power spectrum, then we understand the CMB. So I wanted to look into this for turbulence. So let's start with the simplest thing you can think of. So this, we started with just, where we should all start with Chevalier. So this just a Chevalier ejecta, so a self-similar solution where we have a density profile of the ejecta as one power law to the minus n, the CSM as a different power law to the minus s, and we can run fluid dynamic simulations of this. This is an example from the jet code that we ran that is something like 8,000 theta zones and starts with 8,000 radial zones, but it creates more as needed. So at the top here is density, at the bottom is velocity. And what you're looking at is the Rayleigh-Taylor turbulence as, the ejecta moves into the CSM. So the forward shock would be above this figure and the reverse shock would be below, right? And let's decompose this into angular modes, right? So how we do this is we start by saying any value in this, say density or velocity, can be represented by a sum of spherical harmonics times some amplitudes. We can solve for those amplitudes by integrating. And we can translate this to the power spectrum. And it's a pretty easy calculation to make on models and hopefully on data. And what we get when we do this is a power spectrum that looks like this. So these different purple values are different resolutions of simulation. And we see it vaguely looks like a broken power law, right? So the important thing to remember here, on the y-axis, we have power. On the x-axis, we have L, which is theta equals pi over L. So small L is large theta angular modes. And the character of this power spectra looks as follows, right? So moving from left to right here. Anyways, so at large L or small scale angular mode, this is where the turbulence comes in, right? So this is your Rayleigh-Taylor saturating at different, turnovers. If we have one finger turning over into another finger, and we find, the power goes like L to minus 3.5. This is steeper than what you'd expect from Kolmogorov, so it's a little weird, but we'll get back to that. It breaks at some dominant value of L, which we call L naught, and then we have this another steep thing here. But remember, our simulations are just spherical. Right? They're just spherical and empty. This is where your supernova would put an imprint on the remnants power spectra, right? This is where you would find angular modes from asymmetry or nickel bullets or jets. But can we break this down into physics? Oh, before I do that, I'll say our things are 2D, but it's consistent with the one 3D example I've managed to find, the one example I've managed to find of this in literature. So this is a 3D exponential supernova running into CSM, and they also get a very similar Rayleigh-Taylor saturation rate here of L to the minus 3.9. So that's also steeper than Kolmogorov. So something fun about how Raleigh-Taylor saturates to smaller scale modes is happening there. Right. But let's get back to the power of being able to run these as simulations, is I can run many of them with different values of n and different values of x, right? So this here is the case of a constant density CSM. This is a wind. All the different colored lines are different density profiles of the supernova ejecta. And when we plot them as L over N, they all align, which tells you that this dominant angular mode here, L naught, equals empirically 3N. So this is very cool, and I'll finish in a second here. But L naught equals 3N. And what we think is going on here is what's setting our dominant angular mode is the density scale height of the ejecta, right? So just rho over rho prime. When you do out this math, you get that if L naught is just from the scale height, it's pi over n, pi is 3, I accept it. Very cool. And this is consistent with Don Warren's results too, if you go and calculate what the scale height is for an exponential profile expanding over time. So what does this mean? So if we go back, and these are a couple different of our simulations plotted on the same circle so you can see them, this dominant angular mode, L naught or theta naught, traces out the characteristic scale of the turbulent ejecta, right? It's roughly the width of these Raleigh-Taylor fingers. And if we go back and we look at Tycho, you can see there's a dominant angular mode here. And it's totally just dominated by the density profile of the ejecta. It doesn't matter what it's running into. So this is two really cool things come out of that. One, if I put clumps in the surrounding medium, my power spectra does not change at all, which is weird and cool. And if you don't believe me, see the paper that's coming out imminently. But two, if we go back to 1A progenitors, they predict radically different density profiles for their supernova outflows. So potentially what we can do here is we can take our remnants, look at just what the dominant mode is, add up the powers at different angular scales, and it can tell us about the density profile of the supernova that caused it. So I think this is really cool. I can think of maybe a career's worth of follow-ups to this. And it's a really easy calculation to make both on your data and your models. And I really hope you're as excited about it as I am. So I will leave it there. Hopefully I convinced you. The 1A problem requires observations at many wavelengths at many times, and the continuation of trying to connect models to those observations. Thank you. Yeah.
I want to ask about the early time bombs.
Yeah.
And I think I just want to put the question around. So
Yeah.
if you don't detect bombs.
Yeah.
Does that constrain the double decker?
So there are no bumps for the thinnest shells, unfortunately. So bump tells you something weird's there. Lack of bump tells you there's not anything on top of the ejecta.
And then maybe an extension of that.
Mhm.
I think the plots you showed are sort of like daytime scales.
Yeah.
If we're thinking about shock breakout kinds of things that are like seconds.
Yes, so I didn't include CSM or shock breakouts. I tried to calculate shock breakout for like a double detonation, and it's way too low and too fast for us to see with current technology.
Low and low.
Very low amplitude, very quick. So
Other questions?
So I didn't quite understand about the remnant where you said that, like, you said that there's no difference in the power spectrum if you have a 1 over r squared wind versus a constant density? Or okay, but if you're
Yeah.
I mean, it seems like some of the curves, like n equals 6, for example, is different. Like some of them are shifted to like a slightly.
there is
smaller
jittering. And part of that is at fault of looking at this in these smooth things. So you got to remember that because this is a log scale, right? The change in here for any kind of smoothing thing is much more significant, and these are all going to be much smoother. So it's hard to say, but we did all of these fitting on the raw data that's not smooth, not on this easily visualized wobbly thing for you.
And CL is the amplitude of your, of the, like the amount of power at a given
Yes,
scale.
but that's going to all be relative, right? Yeah, Ellie's barking at me.
I don't think everyone agrees.
But it'll change over time, but okay. So calculating the absolute power of any of this is not going to be something that's terribly standardized.
Yeah, no, I'm just like, like looking at the amplitude of this, the spectrum, the fact that that's different between S equals 0 and S equals 2, I feel like maybe that's an interesting diagnostic here.
This is,
Like,
these are all shifted, right?
uh,
So these are all trying to shift in terms of the y-axis to line up for the same power,
so all the colored lines are shifted.
up and down, but not left to right.
Okay, well, I'm thinking that the green curve on the right for S equals 2 is lower than the green curve.
Yes,
at
but what
S
I'm
equals
trying to
S.
say is any measurement you make from, say, a real remnant has no scale to calibrate it on, right? In terms of what the absolute power is. So saying one is higher or lower than the other means nothing. It's the right way to start thinking about this, but
Did you compare with the measurement of the power spectrum for the contact discontinuity in Tycho that we did back in 2005?
not yet.
Okay. I have it here.
All right, let's do that.
Our guests.
Yeah, so Noam, if you saw my simulations, pretty spherical. So how spherical a double detonation is going to be is about the timescales between that helium wraparound and convergence and how centered it is. But we're, you know, so it's going to be a function of how thick a helium shell you have. But in a lot of the cases, you're seeing pretty spherical. What we're looking at now in our multi-D simulations is quantifying how central that second detonation is and how far off that can be before you get specpol that disagree with 1As. But we're trying to quantify that as well.
Yeah, follow-ups.
I think there's, to back you up, I think there's several studies for polarimetry as
Yeah.
well by Ola. That's.
Yeah.
I disagree with that.
There's a
But I mean,
question.
maybe you're right, that there's a companion transfer mass. You did not simulate that. Did you have the companion there? No.
No.
It's very small.
You're right.
So you could put
Yeah.
the companion there.
You could put a companion there. You could, you know, you're gonna also, you're right, Naomi, we'll see not a perfectly spherical helium shell, but I think a spherically centered detonation is gonna wash out very small scale asymmetries, but it is something to look into.
On that thing.
Yeah.
We'd like to apologize.
That's okay.
Next up, we have a 12-minute talk by Sumner Starfield with 3-minute questions or 10-minute talk.
I think it's 12 plus 3.
Yeah.
12+3.
We appreciate 10-minute talks with lots of question time. But I do appreciate.
Okay,
Great, that looks good.
okay. There's my title, Hydrodynamic Simulations of CO and Oxygen Neon Classical Novae Outbursts. With the bottom line, they're growing in mass, the white dwarfs. And I'm speaking today from my office at home. Today is the first day of school at ASU. And I just thought, for comparison, we have 140,000 registered students today. Give you some idea of what's going on. We have campuses all over the world. Okay, there are my collaborators. At least one, I think, is tuning in as long as I finish by 3 o'clock this afternoon. You probably are familiar with some of the names, except Maitri Bose, who's a cosmochemist. So let me start with a summary of a classical nova outburst. you've heard a lot about supernovae, but let's go to a classical novae. Lasts about a year, radiates about 10 to the 45th ergs. Peak luminosity exceeds L. Eddington. That's fun if you're modeling it. They eject small fractions of a solar mass, and the amount of ejected depends on the white dwarf mass. Speeds from 300 to about 8,000 kilometers per second, and quasi-partition 10 to the 46 ergs. When we look at the abundances, I won't be talking about those today. We find them all far from solar, with enriched lithium and beryllium, both predicted and now observed. Helium is always enriched, and of course, that's a result of the thermonuclear runaway, depending on both the proton-proton chain and the CNO cycle, converting hydrogen to helium. We find from our observations that there are two composition classes for the underlying white dwarf, either carbon and oxygen or oxygen and neon, except of course, when you're studying classical novae, you find there's a outlier, V445 PUP, which was well studied, did not eject any hydrogen at all, and there doesn't seem to be any hydrogen present during the outburst. And novae are emitting very high energy gamma rays discovered from Fermi LAT. We predict radioactive gamma ray emission, but the amounts are too low to be observed by current spacecraft. Okay, they occur on one member of a close binary stellar system. This is a picture of RS Ophiuchi that was actually mentioned this morning. And it's a symbiotic with a red giant transferring mass into an accretion disk, in this case, surrounding a white dwarf, and the white dwarf is busy exploding. And for some of you who follow social media, this sort of looks like the Carrizo picture for the Webb telescope. Anyway, the cause of the outburst is a thermonuclear runaway where the white dwarf accretes gas from the secondary. When sufficient gas has fallen onto the white dwarf, it initiates nuclear reactions. Those nuclear reactions are occurring in a degenerate material, and an explosion results, and we call it a thermonuclear runaway. The accreted gas mixes with the white dwarf to produce a fast outburst. That's an observational statement. And until recently, we weren't sure when, where, and how much of core material was mixed into the accreted envelope. We may still not know that, but at least we've got some kinds of evidence. And again, we know from observations the two different compositions. Now we've already heard from our last superb talk about we need to make predictions that can be observed. And of course, here are some of them from classical nova studies over the last N years. Enriched light elements in the ejected gases were first predicted by our hydro studies in 1972. A rough light curve behavior in the early 70s. Enriched lithium in the ejecta was predicted in 1978, not confirmed until 2015. The X-ray outburst at the beginning, when the explosion reaches the surface, heats it to high temperatures, and it's luminous for a bit, predicted in 1988, confirmed in 2022 by E. Rosita. And finally, the white dwarf is growing mass to a supernova 1A explosion. We predicted it in 1988 for USCO, which had a last eruption on June 6, 2022. And that may actually answer one of Jaco Vink's concerns about the progenitors. Okay, this is the code we use. I'm not going to say very much about this page. It's all published either in our 2009 paper, our 2020 paper. Here's Rafe again, and Christian Iliadis, and so on. Numerics are pretty standard. The microphysics keeps getting improved. Okay, now what about mixing? when does that happen? We're going to use the three-dimensional, finally, studies of mixing a nova done by Jordi Casanova in Barcelona. He's not there anymore, with collaborators studying the fact or realizing that if you take a runaway, in this case on an oxygen neon white dwarf, and you wait and see what happens, once the thermonuclear runaway is ongoing and super, it starts entraining and getting material from below up into the accreted layers. If you follow it long enough, and of course this is a major computational effort, you find roughly sufficient core matter mixed up into the accreted matter. And so we use those studies to guide our studies. Although Jordi Jose has actually taken those studies and converted and put it back and forth with 1D studies. Remind you, you already know this, that the size, the radius of the white dwarf shrinks as the mass increases, meaning that it takes less mass to accrete onto a massive white dwarf than a low mass white dwarf. Okay, why do we consider a broad range in white dwarf mass for cataclysmic variables? More than 0.8, as we heard in the last talk, SF Cygni, but we get up to 1.2 for IM Nor or UGEM. There are other studies not on this transparency that are even higher mass, and that compares to the canonical single white dwarf mass of 0.6. So we have used NOVA in one recent paper and one about to be recent paper. We take the mass accretion rate that's low, but that's what we need to get a lot of mass on. 2 different compositions for the core, 3 different compositions for the envelope, solar, 25% core, 50% core, 6 white dwarf masses, and we either accrete material from the beginning like we used to do, or we accrete solar material until the thermonuclear runaway is ongoing, and then switch to a mixed composition up here. So here is the results for a carbon-oxygen white dwarf. These are, again, the results for, this is temperature, total nuclear luminosity, and solar units, published in 2020. You can see we get to 610 to the 8th Kelvin for the most massive white dwarf with a 50% mixture, 10 to the 14th for the nuclear luminosity, and of course it decreases as we decrease the white dwarf mass. And these are times in seconds. So this is all happening very rapidly. Comparing that to the same set of simulations for an oxygen neon white dwarf, 50-50 only gets to about 350 million degrees. And again, the same decrease as we decrease the mass of the white dwarf. We don't put 0.6 on there because it's just not doing anything very rapidly. This paper is in preparation. Rafe, I'm working on the discussion section, which needs some changes after this meeting. Okay, here's the money plot. How much mass is ejected in the explosion? This is what we call the retention efficiency. It's the accreted mass minus the ejected mass divided by the accreted mass. And for most of our simulations, it's darn near 1. Almost no mass is ejected as compared to the accreted mass. So the white dwarf must be growing. Yes, for the 50-50, which does have some problems, with agreement with observations, I'll show that next, it does eject a reasonable fraction, but not minus, okay? So it's still accreting, it's just growing more slowly to whatever limit you want. So just for fun, here's the bolometric magnitude, that 50% core. Notice it gets up to about -15 for a very short time. That's shock breakout. But all of these models stay very luminous for observations, -10. Mansi Castlewell has a nova at -10, but not very many. For 25% core, these are more reasonable for more massive white dwarfs. The low mass white dwarf never gets very bright. Okay, lithium, about 2 times 10 to the minus 10 for the most simulations. That's solar masses, sorry, 2 times 10 to the minus 10 solar masses for the more massive white dwarfs. If we use that number, first of all, excuse me, compared to Lauders, we use Lauders, we get about 1,000 solar masses of lithium in the galaxy. If we take our lithium from our classical novae work, we get about 100 solar masses. Okay, so that's not a large fraction. Where else does it come from? The observations, look at papers by Paolo Malaro et al. They get about 7 to 10 times more lithium than we had observed than we predict. But hey, that's close enough for astrophysics. There's CO nova ejected matter in the solar system. This is done with Maitri Bose. These red points are actual pre-solar grains that fit our CO predictions, published in 2019. Published earlier, Bob Pepin, who did neon E a long time ago. The asterisks are predictions of neon novae, and the red are anomalous interplanetary grains collected by U2 aircraft. Okay, and you can see they fit pretty well. So there's oxygen neon grains too. And here are our conclusions. The white dwarfs in classical novae are growing in mass as a consequence of the explosion and could be supernova 1A progenitors via the single degenerate scenario, as long as the secondary is massive enough to produce sufficient fuel. I mean, if the mass of the secondary, the large star that fills its lobe, is too low, it's not going to get that white dwarf to any limit you want. Maybe it will, maybe it won't. So not all cataclysmic variables are probably 1A progenitors. And then finally, they produce all the lithium-7 in the galaxy, and I'll stop here.
It's so full of very cancer. But on that question, on that note, we'll have questions. Any online questions? So I have a question. The lithium-7. So can you go back to your population studies and see if, like, how do the abundances compare?
Besides lithium-7?
Oh,
or what?
The lithium-7. How close do we now get to the predictions? To the observer about the predictions from nucleosynthesis?
We predict about 100. The observed amount based on Lauders is about 1,000. But again, the observations imply there's more lithium in novae. I mean, these are observations not only of lithium-7, but beryllium-7 down at 3130. There are some concerns. Actually, we have concerns, and we have an HST proposal that unfortunately doesn't have a bright nova right now, where we want to compare the beryllium-7 to magnesium-2 at 2800 using STIS on HST and get a better concern without worrying about telluric observations. But right now, taking all of the observations of LMC novae, oxygen neon novae, carbon oxygen novae, the observers are finding much more lithium-7 in nova ejecta than we predict. Hey.
Thank you very much. I think on that note, in the interest of time, let's move on to the next speaker. Thank you very much, Sumner.
Okay.
Next up, we have Leila. Is that correct?
That's Leila.
want to talk about study of Tycho SNR asymmetries with three-dimensional velocity vector fields. Take it from there.
Hi, my name is Leila Godino. I'm a first year PhD student in TA Saclay near Paris, under the supervision of Fabio Acero. And I work on three-dimensional dynamics of supernova remnants and X-ray and Chandra data. And currently on the ejecta of Tycho SNR. So why do you need new tools to study the three-dimensional dynamics? Because it's the key to understand the progenitor. Because the origin of the velocity asymmetries can be innate due to the explosion asymmetries or acquired during the expansion linked with the CSM inhomogeneities. The current methodology to study the three dynamics is summarized with this plot, with data from Williams et al. 2017. The study is separated in two parts. There is the plane of sky. So to measure the proper motion, it's the arrow. They use two one-dimensional profiles to measure the little shift between two images from a bright blob. And for the line of sight, so the velocity, they use the Doppler effect with the local spectrum fitting and extraction. It's the color. And they found that there is no clear symmetries neither in the plane of sky or in the line of sight. So there is some limits because there is a very few number of vector and limited spatial coverage. And as there is often the case in X-ray studies, the spectral and the spatial information are totally separated in the study. So I will present you a new methodology to study the velocity in the plane of sky and in the line of sight. And we will begin with the line of sight. For this, we use the GMCA tool. Adrien spoke about this yesterday. So the idea is to decompose the cube, a cube because there is two spatial and one spectral information, a dimension, and to decompose this with a linear decomposition, and we obtain component with spectrum and associated image. It's like a PCA. You can see the spectrum as basis to reproduce the spectrum in each pixel of the supernova remnant. And there is an optimization of the spectromorphological differences between the components. And there is no supervision, but we can interpret the result as physical. For example, here, in input, there is a cube of Chandra from 2009, centered only on the silicon line. And we use GMCA. I ask three components, and we obtain this. And we can interpret the result as physical. The first here can be interpreted as spin contamination. We recognize the power law in the spectrum and the filament structure in the image. And GMCA succeeds to separate it from the two other components because the two others are ejecta with fluffy aspect in the image and line in the spectrum. It's very different. And GMCA even succeeds to separate blue shifted from red shifted emission. We see this with the translation in the spectrum. And we can see that the emission comes from not from the same part in the image. So we use these two information to recreate a map of the energy centroid of the silicon line in all the supernova remnants. So the idea is that thanks to the image and with the spectrum of GMCA, we can reconstruct the spectrum around the silicon line in each pixel, and then in each pixel we can find where is the energy centroid. And there is a total coverage, and it shows that there is a large scale asymmetry between the south, we are more redshifted than the north, we have more blue-shifted. And then we can use this little formula to transform our energy centroid map in a velocity in the line of sight map. There is a big hypothesis for this. It's for the energy at frequency. It's the energy at rest. I will speak a bit about this later. And we can see that our result is brightness independent. In the black, it's the control of the silicon emission in X-ray. So the limit for this is that we obtain integrated value in the line of sight, and there is no uncertainties in GMCA complicated enough, so there is no uncertainty, and there is description of the energy of references. And we can check our results with other local studies, and we can see that there is a good agreement. If we take our value in the map in the same zone that obtain the velocity in the line of sight with Doppler effect, we obtain a very good agreement. And for the question of the energy of references, I create a map with theoretical position of the energy at rest, energy centered at rest of the silicon line, according to the temperature and ionization rate. And on this, the little point, I put some measure of temperature and ionization rate that we obtain with fitting in a local zone. And we can see that the energy centered that correspond are very in the same zone. So we take the mean and we use it as references. And we can also find that there is a small impact of the variation of the energy of references. So for now, we use this hypothesis. So it was for the line of sight. Then I will present you another method to obtain the velocity in the plane of sky. For this, it's inspired by the optical flow, but we adapted this for the Poisson statistics. The idea is to do a profile with two-dimensional, with three images. So the first step is to find a lot of good features to track in the image. In the first image, you take this as a references and do a little boxes around your feature. Then you take the equivalent of this boxes in another year, and step by step, pixel by pixel, you calculate the good match between this and this. For this, we use a statistic, and we obtain a true landscape of statistics, and the minimum in this landscape correspond to the better match. And we deduce so the shift and the velocity in two dimensions. And we deduce this with subpixel precision because we do 2D interpolation, and with a complete uncertainties ellipse. And the algorithm is not a black box because I put it. And so we obtain this. We obtain hundreds of vectors, thousands in this case, that allow the statistical study. And for each of these vectors, there is an ellipse of uncertainty, not shown here for obvious reason. And it corresponds to a local behavior. That's why it can be a bit noisy in the middle. And as expected, the velocity are higher in the edge than in the center, because we expect spherical expansion, and the projection is higher in the edge. So if we do a quick view in the multi-wavelength context, we forward track a measurement by Capsuda et al. 2010. There was an asymmetry between the southwest and the northeast that was shown. And this asymmetry was explained with Williams et al. 2013 with a density gradient in the other side. And there is also local particularities. For example, here there is a potential molecular cloud, and we can see that in the same zone our vector field is slower, and it's the same here where there is band emission, so potential interaction, and it's the same idea. Our vector field is slower, and in contrary, here there is fast iron and silicon blob, and we have a faster vector field. And to understand a bit better our results, we can do this. So polar plot. All the points are our measurements from the image just after. It's only the edge, and there is a comparison with the velocity of the power shock from Capsuda et al. 2010. And the first thing is that we don't see the same clear big scale asymmetries than from the power shock, and there is this strange behavior where in the half of the spinal remnant, the ejecta extension are sometimes faster from the power shock. So perhaps there is an interruption, and in this faster zone, there is two behavior. There is some jets in red with a normal overall speed. So there is a faster vector in a bigger radius, and there is some anomalies in blue here, where there is a faster zone in a smaller radius. And for example, if we study one of them, and if we do the profile, we obtain this. So it's the velocity in the plane of sky according to the radius. We expected, in the case of the spherical expansion, we expected a linear increase. And so you can see that it's not the case. There is an increase, but there is a slowdown. So perhaps there is an interaction with the cloud in the zone. And one of the interesting things is that we can do a 3D analysis, because we can see that there is a correlation with the velocity in the line of sight that we obtain. So all this methodology are summarized here, and it's a very, very coded plot, and I think it's a message. So to summarize the methodology on the line of sight, we use a cube decomposition with GNCA. With the input of GNCA, we reconstruct a map of the energy centroid and integrated velocity in the line of sight. And we've shown large-scale velocity asymmetries. And for the plane of sky, we use a new method, the measure proper motion with 2D profile, and we obtain angular vectors, and perhaps some anomalies and some proof of interaction. And so a lot of information to use to better understand the 3D dynamics. So thanks for your attention. Happy birthday, Tacos SNR.
20 seconds to spare.
That's fast.
It's inverse seniority.
Nice talk. Thank you so much. In your slide where you talked about velocity in the in-plane of the sky velocity, you mentioned the C-stack function.
Yes.
Could you elaborate a little bit on that? What is that function exactly?
So it's an alternative of like range function, but it's adapted for the Poisson statistics. So there is a formula, I don't know, but it's special for the Poisson statistics. It's a bit better. Thank you.
I mean, are you raising your hand? You would win against that?
I am, but you can go with.
Go ahead.
Okay, all right. In the place where the gradient, where the velocities are lower, do you see any sign of interaction like in radio or something?
Which velocities?
It like
The plane of sky or the line of sight?
the I forget which slide it was, but you had the red and blue arrows.
Okay, so it. I think so.
Yes, I guess plane of the sky. Yeah. So yes, in the direction of that molecular cloud, do you have
Yes.
any sign of interaction?
So there is an article with an interaction, a potential interaction. So I didn't check, but I think it's a very good idea to do a multi-rate lens to study and better understand, to use our results. So, but yeah, there is normally in radio or something here, but just here. So it's a bit strange. You don't explain all the anomalies that we see.
On that level, okay. So it's a very nice talk. There was a paper by Sato and Hughes a few years ago where they tried to do something very similar. Are your results consistent with theirs? She did show that. I must have been looking at the paper.
For the line of sight, I think. Yes, we use the Williams and Sato result.
Okay, thank you. Sorry, I saw the wings.
Yeah. It
So
was
it's perfect.
very complementary with the 12 curves.
Are the velocities accurate enough that you would be able to measure velocity gradients and things like vorticities from the Rayleigh Taylor instrument? Or is that completely out?
I hope so, but in the plane of sky, we didn't see this. There is some turbulence, but uncertainty. For example, here there is this iron blob, so it will be possible that it was vortex, but no, we cannot see this. It's a bit difficult.
the last 20 seconds, I'm gonna take before we ask the question. It's very nice use of optical flow, like not very few people have done this. So great work. So one of the things that I'm obviously very interested in is where's the center? Can you give us a center with uncertainty? And
Yes.
have you published that?
No, not yet, but it's the project. In my last presentation, I did it the center, and we find something more like the geometrical center, like the Warren results.
Okay.
And it was, yes, more geometrical than the offset results of Williams et al. 2013.
We'll go back to the symbol.
Thanks, Will.
Thank you very much.
Thank you.
So, I would like to introduce John. Josh. 12 minutes, that's your geared up. Give me one second.
Not bad. Get a story open here. It just goes to the side.
Take it away, Josh.
Okay, hello everyone, I'm Josh, thanks for your attention. I am a graduate student working with Wolfgang Dwarf at Michigan State, and today I will be presenting work that I did with my collaborators, Wolfgang Matosek Kenshin, Russ Twanto, Jessica Liu, Andre Pollard, Giovanni Sternpelli, and Alfredo Zenteno. Okay, so we've heard many times over the last couple of days, the type 1a progenitor problem persists. In other words, white dwarfs explode and we don't know why. We understand that they come from the explosions of carbon-oxygen white dwarfs, but that's about where our understanding ends. We have many progenitor scenarios, and we are doing our best to try to disambiguate between them. There are two large scenarios that you are probably generally familiar with, primarily the single degenerate accretion scenario and the double degenerate merger scenario. We've heard many talks from ways to try to figure out what we're seeing from early light curve bumps that we've seen or looking for surviving companions. But very generally, I will not be talking about either of these scenarios today. Instead, I'll be focusing on a third scenario that we heard a lot about from Abigail Poland in much more detail than I can give right now, and it was wonderfully done. But to give you a quick refresher, in this scenario, we have a more massive carbon-oxygen white dwarf and a less massive secondary helium white dwarf on the path to merger. Before you get to this point, you get unstable accretion that gives you a thin helium shell that surrounds your primary white dwarf. Before the primary or before the secondary can be tidally disrupted, you get a detonation that runs around the entire primary and sends a shockwave around it. That shockwave converges near the center of your primary and gives you a second detonation that gives you your thermonuclear runaway, fully engulfs the star, and gives you something that looks quite like a type 1a. So let's be ambitious. Let's start out by asking, what if this scenario explains the bulk of type 1as? What will we see? And in general, how can we try to falsify this prediction? The easiest thing to do would be to try to identify these progenitor systems directly, just by looking for these double white dwarf systems. But unfortunately, that's basically impossible to do. These double white dwarf systems are just not luminous enough with our current observing capabilities and the volume that we can probe. You cannot detect these systems. A recent paper showed that you have roughly a 0.1% chance of observing these things with our current observing capabilities. You can do population synthesis work and delay time distribution work as well to try to figure out whether these things give you the right rates for type 1as and in the right timescales. And we've heard a little bit about that earlier in the conference as well. These seem to generally agree and they seem to generally work out, but there are large uncertainties in a field that this is ongoing work. We don't have the answer here yet. You can also use polarimetry to try to probe asymmetries of the early system of your supernova and ask whether it's generally symmetric. This also seems like it works out, but there are uncertainties here as well. My personal favorite way of trying to probe this question is looking for surviving companions that are predicted as a result of this scenario. Specifically, because your primary explodes before the secondary becomes tidally disrupted, the secondary will be ejected from the system very quickly and significantly over luminous, because it has to be very, very close to the primary in order to get white dwarf mass transfer. And because the supernova ejecta runs into this white dwarf, it becomes significantly over luminous. So this prediction is what will be the focus of the rest of my talk. Chanel 2018 went looking for these types of stars in Gaia just by looking for the highest proper motion objects, using parallaxes to figure out distances, and then figure out what the tangential velocities of stars were just across the entire sky. They identified 3 stars, which very interestingly have very, very peculiar colors, bluer than the main sequence and high above the white dwarf cooling track. The discovery of these stars is a huge reason why this scenario has garnered so much interest, and so many people are interested in testing whether this is the progenitors of type 1As. So where do we go from there? These 3 stars were certainly peculiar and interesting, but because they were just discovered in the field, they're very difficult to tie directly to any given type 1A. They could just be weird stars created in some other fashion. But can we do better? Can we try to identify one of these stars associated with a type 1A? So this plot here shows how the orbital velocity of your secondary scales with the mass of that secondary. And we are particularly interested in this region here, showing how this orbital velocity scales for white dwarf companions. We can see that in order to get mass transfer from your secondary onto your primary, you have to have an orbital velocity of between 1,000 and 2,500 kilometers per second. This is the same velocity that you would expect the star to inherit after the primary explodes. So we have our experiment. We're looking for an overluminous white dwarf, which still puts it as faint as about 1/10 of a solar luminosity, moving at least 1,000 kilometers per second. Where can we look? It turns out that there are 3 reasonably observable supernova remnants that we've talked a lot about during this conference. There's Tycho, Kepler, and SN 1006. Unfortunately, both Tycho and Kepler still lie pretty close to the galactic plane and lie behind multiple magnitudes of foreground extinction. As a note, I wouldn't take these absorption values at face value. These are just line of sight estimates and aren't probably directly applicable for these remnants, but they give us a good idea and show you that both of them lie behind a prohibitive amount of foreground dust. So we really have a hard time looking for faint blue objects inside. SN 1006, however, is much more promising. Because it lies high above the galactic plane with a latitude of about 15 degrees, there's little foreground extinction and also very low source confusion. Both of these things aid in performing high precision astrometry. So that is exactly what we did. We gathered a 4-year baseline study of the SN 1006 remnant with the dark energy camera and combined those observations with Gaia in order to extract stellar proper motions and try to identify a hypervelocity white dwarf. This green circle shows the distance that a 2,000 kilometers per second object could have traveled since the time of the explosion. But we wanted to be very careful and we wanted to make sure that we wouldn't miss the star. So instead, we examined this red region just to allow for strong ambiguity on the center of the remnant in the possible case that the geometric center and the site of the explosion were significantly offset. So here are the results of that survey. These pink points are the same Chanel 2018 objects that I've mentioned before, except placed in the remnant to give us their expected properties there. They lie comfortably in this light blue region, which is the parameter space that we examined in this survey, going down to an R-band magnitude of 21 and a projected velocity of 600 kilometers per second. One more note that I forgot to mention. In order to get from proper motion to projected velocity for the purposes of this plot, we assumed that all of these stars lie at the distance of the remnant, so we don't have to trust parallaxes in case they might be wrong, especially if it could be a problem for the fainter end of the distribution. These 4 purple points are what we came up with. The 4 objects that could possibly have been these surviving D6 companions inside the remnant. I do want to point out that because they are already significantly lower than the velocities that we were expected, they already are relatively weak candidates to be the surviving D6 companion. But we did more. We followed them up. Because all of these stars exist in Gaia, we are able to just ask what their colors are, and we can compare them to these previous 3 Genedal 2018 stars that I keep bringing up over and over because that's what we're trying to compare to. Once again, I've said this before, but the Genedal 2018 stars are very blue and high above the White Dwarf Gold track. The 4 stars that we discovered instead lie relatively on the main sequence and are just not particularly convincing D6 companions here. They're more likely just foreground main sequence stars. So where does that leave us? We did not discover an obvious surviving companion in SN1006. We wanted to be thorough. We wanted to make sure that there wasn't any reason that we could miss it. And we came up with 2 significant reasons we wanted to investigate. First, could the star have been hidden because it was shot out relatively close to the line of sight? Because this was a proper motion of survey, we wouldn't have been sensitive to this possibility. The second possibility is whether it could have been hidden by some unforeseen dust absorption, say by the remnant itself. We wanted to investigate both of these possibilities. So to investigate this first possibility, we just shot out a 1,000 kilometers per second object in a random direction and asked ourselves, what is the velocity we would have observed, and how likely were we to have missed the object with our sensitivity limit of 600 kilometers per second? We found that there was about a 6% chance of this happening, but I really want to stress 1,000 kilometers per second is a lower limit on the velocity expected for one of these stars. And any additional velocity that you gain very quickly shrinks this parameter space. For instance, a 1,200 kilometers per second star only has about a 3% chance of being missed. So to investigate that second possibility of the star being hidden by some unforeseen dust, we investigated these Guo et al. 2021 dust maps that look at stars at different distances and try to reconstruct a 3D distribution of the dust for the southern sky. This red region, once again, is just our search region to guide the eye. As I've mentioned before, there is some noticeable but very little foreground dust. And then we can go ahead and ask, well, how much dust is there inside the remnant itself? We took a 0.24 kiloparsec absorption slice of the additional extinction accrued as you move across the remnant and asked, is there any additional dust here that could hide our star? We really didn't find any, less than 1/10 of a magnitude, and we came to the conclusion that if you're going to hide this star with dust in some way, you would need to have it be on very, very small scales that wouldn't have shown up in this analysis. Perhaps something like a stellar wind, but you would need some model to tell us why this could actually happen. So where does that leave us with the D6 scenario? Once again, we're pretty sure that there is no D6 companion inside SN1006, but maybe this is just a larger piece of the puzzle, and maybe this is something that we can accommodate. A recent result by Packmore et al. Showed that in this double detonation scenario, it's possible that the secondary doesn't actually survive the explosion, and that would explain the absence of a companion in this remnant. However, as we've seen earlier, it's also possible and even likely that type 1a supernovae are not a homogeneous class. This plot just showing the peak magnitude and decline rate of your supernovae shows that there are multiple clusterings in the space, and that's thermonuclear supernovae span over a factor of 200 in luminosity. It's likely that they have different progenitor scenarios, and that some might be created by the D6 scenario and others might not. To very quickly finish up and just talk about some current work, I have turned my sights to the Large Magellanic Cloud, which I'm sure many of you are convinced is a wonderful place to search for surviving companions. We heard some work earlier today by Xuanhui Li, looking at some of this work, looking at Muse cubes to try to identify surviving companions, and I intend to pick up this work and do more because there are more remnants here left to analyze. Thank you for listening. That's my talk titled Investigating the Type 1a Double Detonation or the type 1A double detonation scenario in the SM1006 galactic supernova remnant, or as a snappier working title, no surviving V6 companion in SM1006. Thank you.
I just wanted to ask, now that D3, Gaia D3 is out, have you looked at the stars from Jennifer again?
It's on the list of things to do. I've looked at DR3 a bit, and most of the parameters that we care about for this purpose really haven't been updated too much. We did get interesting more radial velocity information, which I don't think I've had a chance to look at yet, but it's definitely something that I'm interested in doing soon.
We have the parallax.
So the parallaxes did really not improve particularly much between EDR3 and DR3.
Are you talking
Is-
about the Chanel stars or the stars that Joshua?
Actually, both sense.
I think Ken looked and like it hadn't changed anything.
If anything, some of the velocities have gone down a bit from DR2 to DR3, but
Also, I don't know if SM1006 has multi-epoch Hubble observations or something, but one of the things I've done for my remnant is to look at each after observations of the 10-year epoch, and we do still see some stars moving inside for the remnant I was studying. I don't know if there's HST data for SM1006. You can do.
yeah, I'm not sure. I haven't looked at Hubble data for this remnant, but that sounds like something super interesting to take a look at.
I don't think there's anything inside the realm.
Okay.
Maybe Hubble data.
I mean, I think like ultimately the Deccan data, I think is very deep. So like, no, it goes deeper than I think like any other observations or it exists. On that note, unless there's other questions, let's then catch up.
Can we get the mic, please?
Oh, I took it. It's mine.
I will get this set up since it's a little tricky.
You could have just unhacked one of the hits on it.
And we have a question now, but it's we'll get to it on Slack.
Awesome. Hello, everybody. My name is Travis Court. I'm a fourth-year PhD student at the University of Pittsburgh. I work with Carlos Bananas on modeling the X-ray emission of type 1A supernova remnants in different circumstellar environments, which is a bit of a mouthful. So before I talk about these circumstellar environments, I should tell you a bit about the 1A remnant models, what we can learn from them, so on and so forth. So this plot has been brought up beforehand, but in a 2014 study, Yamaguchi et al. Found that if you look at the iron K alpha centroid energy and line luminosity, that you have a really good way of classifying supernova remnants. We have type 1A on the right in red circles and squares, and core collapse on the left in blue circles and squares. And so this gives us sort of a diagnostic tool if we run a explosion model through an ambient medium. So these shaded regions here, they found that you can broadly explain 1A remnants using uniform ambient medium densities. So the goal here is to sort of see how much circumstellar interaction we can get away with and plot that on this plot. So if we find that there is a lot of interaction, then potentially our circumstellar medium might not work. It'll be too close to a core collapse, not a good 1A remnant. So how are we doing this? We're doing a sort of sweeping parameter space study using 1D models in CHN, where we can model the hydrodynamics and the non-equilibrium ionization. And then we are playing with our circumstellar interaction. And we're not just looking at the iron K alpha centroid energy, we're looking at other bulk properties, such as the ages and the radii of these remnants. And that's all to answer this question of, do broad cases of circumstellar interaction models fit this zeroth order classification. So now that I've teased it a bit, what interaction are we most interested in talking about today? It's been a hot topic of this conference. I'll be talking about type 1a supernovae inside of planetary nebula. So first, the physical reasoning for this, also called SNPs. In the double degenerate type 1a progenitor scenario, as we've learned many things about, you have some sort of common envelope interaction. This interaction would be between our white dwarf and an AGB or RGB star. And we know it's a common envelope because main sequence binaries are sort of too long for this to happen, for this merge or collision to happen. So we have to lose some mass, lose some angular momentum, bring our stars closer together. So this mass will be ejected primarily along the equatorial plane. And that remaining mass will sort of give us a cocoon-like structure. And this cocoon-like structure would be then ionized by our exposed core. And that would give us a bipolar planetary nebula structure that would be close to our exploding white dwarf. Also, this mass that is ejected may not fully be ejected from the system and could cause that in spiral and then have our white dwarf emerge shortly after the common envelope. The remnants are a perfect test for this because what better way to look at circumstellar interaction and an ejecta than a supernova remnant and X-rays. So these are our common envelope cocoon models. They were made by Guillermo Garcia Segura et al. In 2018. They are very pretty. So what we have done is we have two different delay times from the common envelope before we're exploding our supernova. We have our young model, which is 1,000 years delayed. We have our older model, which is 10,000 years delayed. Very creative names. Since we're mainly interested in parameter space study, these are sort of our bookends. Also, to build a bit more depth or breadth of our grid, we're just taking the equatorial model in purple and the polar model in red right here. And these are density plots. I don't remember if I said that or not. I also have 1D projections of these models. The young planetary nebula model is solid line with the polar and equatorial in red and purple respectively. And same with the old planetary nebula in the dashed dotted lines. And so what we have is we've taken not us, but Guillermo Garcia Segura took these high resolution common envelope models, evolved them hydrodynamically and with the ionization to give us a realistic grid of planetary nebula-like structures that are directly tied to this common envelope evolution. So what do we find happens? So this is a similar plot to what I showed earlier, the Yamaguchi plot, where we have the type 1As on the left and the core collapse on the right. Now, instead of shaded regions, what I have done is I just have some tracks, and these are from the equatorial projections. Partially because it's easier to view, but there is a good argument there where if you were to look at any emission measure average quantities, we'd be more likely to see closer to where the equator is because it's much more dense than the pole. So that's why I've just shown the equators. And what we can see here is that whenever we're looking at the young planetary nebula, meaning 1,000 years post-common envelope, after an age of about 150 years, the centroid energy is way too high. It is way more similar to a core collapse supernova than a type 1a supernova. So this should raise some red flags. However, whenever we look at the old planetary nebula model, we see that there is some pretty good, albeit vague, overlap. I'd especially like to highlight Remnants 0509, Kepler and Tycho, because it wouldn't be a 1A talk without mentioning one of them. And we see that there are especially close to the ages that we have for the tracks. The triangle is of around 400 years, and these objects are all between 400 and 500 years themselves. So we have this overlap between our old planetary nebula and our type 1A remnants using this 0th order classification. I'd also like to highlight some really cool chrism spectra that we've involved thanks to the magics of PyAtomDB. And to really illustrate the differences between them, I've chosen two very far endpoints of this plot. We have a very unionized model from our old planetary nebula, that is the light blue arrow and medium right, stage right. And the dark blue arrow is a very highly ionized from the young planetary nebula. I mean, these are about as different as you could get. We have higher ionization temperatures or ionization timescales. We have more lines. We have a higher centroid energy. What else is there to say? So what about the other bulk properties? So up top again, we have the iron K alpha luminosity, but I've added two more plots to this Yamaguchi plot. I have the radius and then I have the age. And we see the same overlap. I've circled the same three objects, so 509, Kepler, and Tycho. And so we're about bang on with this old planetary nebula model. Now I've also added the shaded region. The dashed line is the polar projection from the old planetary nebula model. So you can really see the overlap with your own eye. And I would be remiss if I did not mention that the other 1A explosion models, we see the same trend. Not going to delve into all that because Abigail did such a great job. So ultimately, do type 1A supernovae explode in planetary nebula? To answer that question, we created a grid of 1D hydrodynamic models to explore this parameter space of common envelope cocoons using a young and an old planetary nebula. We've investigated the bulk properties, meaning the age, the radius, and the iron K alpha centroid energy of these models, and we compare them to the observations. And in this framework, we found that there has to be a significant delay between the common envelope ejection and the supernova explosion. And we can say this because our old planetary nebula models were much more consistent with the bulk properties of our 1A remnants, while our young planetary nebula models are way too dense for this observable behavior. So we could potentially say that the delay between common envelope and supernova is probably greater than about 1,000 years. Thank you for your time. I'll take any questions.
Loads of tough questions, which I love. I guess you're the lead senior. Can you say anything about the evolution of that iron K line centroid from shock surface stellar material versus shock ejecta in those models? Because there's a lot of keep going. Yeah.
Up here.
That one. Like in the 10,000-year-old one, you're not really doing anything for the first 100 years or so. 200 years, almost 300 years. But clearly there's interaction. So is that interaction because of core shock interacting with the circumstellar equatorial disk, or is it because the reverse shock is moving into the ejecta?
Could you rephrase that?
Can you decompose that into two parts?
Yes, I could definitely. I have not yet, but that would be very easy.
I think that would be very illuminating because you've got a very complicated interaction there. So.
Yeah. We'll put that on our to-do list for tomorrow.
There might be, if you click on the Q&A.
That's for Josh.
Oh, that's an old one. Okay. I might have, okay, that's we answered this already. So I didn't. I'm gonna say something, then maybe you will tell me if I understood you correctly. You're essentially saying like, planetary nebula, like having a planetary nebula and having exploding inside does not work for 1As. Essentially, you need to have at least 1,000 years. And if I sort of like, take this to the extreme, would this mean that if you merge before you eject the common envelope, sort of like within before you eject the common envelope, so if you merge within the common envelope, would this mean that this is not favored by remnants?
Yeah, so basically,
are you rolling out a double degenerate? Some people might call it 4 degenerate scenario. I know it's a provocative question.
Yes, it is a quite a provocative question. Essentially, what we would say is that anything where the delay is less than 1,000 years, but post common envelope, between the common envelope and the supernova, we would expect it to be way more dense. And so we would just see this get even more core collapse like.
Okay.
Is that
I wonder if someone wants to stand up for the core degenerate scenario. Online, maybe.
I will comment, I've knowing a thing or two about this model, that I don't know if we can really trust the top one, because there's probably strong reason which change the track quite a bit.
Okay.
that's
Or it becomes very challenging to have a lot of slow moving material, because you end up in the blue region.
Yeah.
No matter what.
Slow moving materials such as would be ejected by a common envelope, for example.
A slow wind would have the same effect.
Any other questions? No, I would like to thank all the speakers. They all kept on time, Jackal. That'd be wonderful.